So question 1 says, in the combustion of hydrogen gas, hydrogen reacts with oxygen from the air to form water vapor.
Okay.
If you burn 29.6 grams of hydrogen and produce 265 grams of water, how much oxygen reacted?
Okay, so is that right there? What I wrote?
Yeah,
Hydrogen
correct.
plus oxygen goes to water, and then you have 29.6 grams, and then it produced 265 grams of water, right?
Yes.
Okay, that's the easiest way to do problems with that. Just write down so everything's in front of you. So you had 29.6 grams of hydrogen, and you got 265 grams of water produced. You want to know how much oxygen gas was consumed, right? That's the basic question.
Yeah, it's asking how much oxygen reacted.
Right. So how much oxygen?
So it's asking.
Right. So here's our chemical equation. It's a chemical reaction. The reactants are always on the left. The products are on the right. There's a law in chemistry. That's the law of the conservation of mass. Okay? You cannot create or destroy mass with a chemical reaction. Okay? So you can't create or destroy mass. Okay? You can with a nuclear reaction. We're getting nuclear reactions in chapter 16. With a chemical reaction, you cannot create or destroy mass. So that means the mass you start with has to equal the mass you end up with. No way around it. Okay? So if you end up with 265 grams on one side, you have to have 265 grams on the other side. So if we take 265 grams minus 29.6 gives you how much oxygen you had to react with. Okay? Because it has to be the same. So if you take 265, is it 265.0?
Let me check. No, it's just 265 grams.
Okay. So 265, it would be, let me get my calculator here. This is, you take 265, subtract 29.6. Yeah. And that comes out to 235.4 grams of oxygen. Okay, there we go. Okay, you're only good to one place before the decimal. Okay, so it comes out to 235 grams of oxygen. This is what you need. This 235 plus 29.6 gives you 265 grams of water. The mass has to be the same on both sides. Okay, you cannot create or destroy mass in a chemical reaction.
Okay, that makes sense, because I was overthinking it because I was considering the law, so then I overthinked it, and then so I was like, so that means that yeah, because I was looking at the chapter while doing the homework, and I was just like, so does that mean that technically it's gonna stay at the 29.6 the way it started, since you can't destroy it? So yeah, but I understand now. That makes sense.
Yeah, well, just don't make it harder than it is. Most students do.
Doctor, do we get rid of 0.4 because of the number isn't because of the significant numbers?
Yep, because significant figures. Remember the rule when you're adding and subtracting, you're only good till the least accurate number. This is your least accurate number right here. This is one place to the left of the decimal. So your answer can only be one place in the left of the decimal. You can't go past it.
Okay, thank you.
If it was 265.0, then it would be 235.4. But you cannot make your numbers more accurate through mathematical manipulation. Okay. Do you have another one, Cassandra?
Oh yeah, I'm sorry. I'm logging back in. I don't know why it logged me out.
Oh, no problem at all.
Yeah, I had a question on number 2, and I'll get right to it once I bring it up right now.
It's all right, no problem. Like I said, we're going to use that law of conservation of mass for a lot of things, for balancing chemical equations, for everything else. When we do that, we use a law of the conservation of mass. You can't create or destroy matter.
Okay, so for number 2,
Okay,
It says, use the law of conservation of mass to answer the questions. So it says, consider a hypothetical reaction in which A and B are reactants and C and D are products. If 13 grams of A completely reacts with 24 grams of B to produce 13 grams of C, how many grams of D will be produced?
okay. So is it 13.0 or just 13 or 20, what is it? Are those your numbers?
Yeah, the numbers are 13 grams, 24 grams, and 13 grams.
Okay, so 13 grams of A, 24 grams of B. These are your reactants. Reactants are always on the left side. Products are what you produce, are on the right side. Okay. So the law of conservation of mass says the mass has to be the same on the left side and the right side. You can't create or destroy by chemical reaction. So 24 plus 13 is 37 grams total on the left. So you have to have 37 grams total on the right. So 13 plus what gives you 37?
24.
Will it be 24?
24 grams, right?
Okay.
You have to have 24 grams of D because it has to equal 37 grams. Is that making sense?
Yeah.
I'm glad you're asking you, so we're
Yes.
gonna go over this a lot because you've got to understand it, because balancing chemical equations will be a big part of this class, because you have to do that before you can actually use the math to do the equation, do the problems. So you've got to have a balanced chemical equation. And to do that, you have to understand the law of conservation of mass. Okay? You cannot create or destroy mass. So the mass on the left has to equal the mass on the right, which is the same thing for elements. If you have 5 grams of hydrogen on the left, you gotta have 5 grams of hydrogen on the right. You can't change your elements. Okay? They have to balance. And we use that law in balancing chemical equations. And later on, I think it's chapter 4 or chapter 5 that we do that. Okay. Does that make sense to everybody?
Yes, sir. I have a
Yes.
question relating
Sure.
to atomic mass unit. I don't understand how or what the formula for it is, because it says a unit of mass equals to 1.66 times 10 to the negative 7 kilogram.
Right.
I'm just wondering if this,
Right. Atomic
What are we
mass unit is just a unit we use. We measure things in grams, and we weigh out in grams, right? If you're going to measure protons, neutrons, and electrons, you can't use grams because it'd be like 10 to the negative 24. I mean, it's going to be a real tiny number. So we use this called an AMU. And roughly a proton is 1 AMU, a neutron is 1 AMU, and an electron is very, very tiny. It's almost 0 AMUs. It's just a way of describing a very, very small mass. And we're going to use that with protons, neutrons, electrons when we talk about the atom. And we will go over that in this chapter, because there's a difference between atomic mass units and then the average atomic mass, and then atomic mass and atomic mass units. The atomic mass unit is just terminology that we can use to measure something that is very, very, very small. That's all it is. Does that make sense?
yes, doctor. So if you asked us to weigh a proton or neutron, we can use this formula you're saying, but not
Sure.
for electrons.
Yeah, you can. Electrons it's just really smaller. So in other words, a proton is around 1 atomic mass unit. Just it makes it easier to use calculations with it. A neutron is about 1 atomic mass unit. That's a U. Okay, and an electron is about 0 atomic mass units, like 10 to the negative 4, 1.0 times 10 to the negative 4. That's what we roughly use in how an atom's going to weigh out. And we use that when we predict the isotopes of an element and things like that in the periodic table. But we'll go over that today too. But all this, don't get confused with it. It's just terminology to allow us to compare very, very small numbers. Something that weighs a very tiny amount.
And do you want us to remember Bohr model and quantum models, or
No,
Is
because
that-
those are used to incorporate into the theory of the atomic that we have today.
Okay.
We use the Bohr model and all the different experiments that went along with that to predict what we have today as the atomic theory.
Perfect.
Did that make sense?
Yes, doctor.
Okay, perfect. Other questions?
Yes, sorry, I was just pausing so I could give somebody else a chance just in case.
No, I think that's great. That's why I'm here. The questions you're asking, I guarantee you, other people have the same question. Guarantee you.
Okay, so my other question is another part from the homework. So
Okay.
I'm gonna go ahead and read it to you.
Sure.
So it says a 3.8 gram sample of sodium hydrogen carbonate is added to a solution of acetic acid weighing 10.4 grams. The two substances react, releasing carbon dioxide gas to the atmosphere. After the reaction, the contents of the reaction vessel weighs 11.7 grams. What is the mass of carbon dioxide released during the reaction?
Okay. So we got sodium hydrogen carbonate and we got hydrochloric acid. We got 10.4 grams of hydrochloric acid and we got 3.8 grams of sodium hydrogen carbonate. So on this side, we have a total of 14.1 grams, right? 3.8 plus 10.4. That's our total mass of our reactants. Okay. We're releasing carbon dioxide gas into the atmosphere. And what's left in our container weighs 11.7 grams. That's what it says, right?
Yes.
Okay. So let's look at what we've got. We've got a total mass on this side is 14.1. We've got a total mass at 11.7. We know those have to be the same. The only thing we've lost on the right-hand side here is CO2 gas. So since you've lost that into the atmosphere, you're not weighing anymore. What does that CO2 gas have to weigh? Remember, both sides have to be the same with the conservation of mass. So how much gas do we lose to the atmosphere? Is that
2.5 grams, I believe.
14.1 minus 11.7, which comes
It's
out to what?
14 I think it's 14.2, doctor, I believe. I calculated it to 4.
I did. You're right. You're right. That's my fault. 14.2. That's why I use a calculator. I make simple mistakes.
So I think it comes out to 2.5 carbon dioxide is released in the air.
So 2.5 grams of CO2 is released into the air as gas. 2.5 plus 11.7 comes out to 14.2. So your answer would be 2.5 grams of CO2 had to be released. Because the mass has to stay the same. Okay. Always write it out in front of you so you can see what it looks like. And sometimes it makes it a little easier to follow.
Yeah. Yeah, thank you for that. It's because I'm more of a visual learner. So once like I see it visually, then I get it right away.
Me too. I'm the exact same way. When I took exams when I was in organic chemistry, my page looked like it had road maps everywhere. I had pictures and because I have to see it. If I see it, I can understand it. If someone reads it to me, that's not write it down when you read it to me. Someone can read it to me all day long and it doesn't mean anything to me. If I write it down, put it in front of me, and I can visually see it, I understand it. And I do the exact same thing. That's exactly how I work. I have to be able to see it in front of me. I'm a very visual learner.
Okay.
That makes sense, Cassandra?
Yeah. So I had 2 more questions if anybody else has any questions before I continue.
Anybody else have any questions, or we'll let Cassandra keep going? She's doing great. These are perfect questions.
All yours, Cassandra.
All right, go for it, Cassandra.
Okay, so this next one is pretty lengthy, so I'm gonna try to read at a good pace so I don't confuse everybody.
Okay.
So This one's question 29 of 32 in chapter 3. It says, the image shows a representative sample of 50 atoms of a fictitious element called lemonium. Lemonium consists of 3 isotopes. The red spheres are Le19, the light blue spheres are Le17, and the dark blue spheres are Le15. Determine the percent natural abundance of each of the 3 isotopes.
Okay. You have to see the picture. Okay. Le19 is what color?
Let's see. It's red.
Le19 is red. Le17 is what color?
It's light blue.
Okay, we'll go with blue. And then Le15 is what color?
Dark blue.
I don't have a dark blue, darn it. Okay. Dark blue, light blue, and red. All right. Can you count the number of dots or the number of atoms? There's 50 atoms, right? Yet 50 atoms total, right?
Yes.
How many atoms of those are red? Just count them. Just sit there and. How many red atoms do you have?
It shows 16.
Okay, so you have 16 red ones. How many light blue ones do you have?
Let's see. Sorry, they're kind of crazy scattered.
Yeah. Or is it easier to count the dark blue ones? Whichever one's
Oh.
easier to count?
They're 20. For the light blue, it's 20.
Is light blue 20? So if you count the dark ones, you're going to have 14, right?
Yeah.
Because it has to total 50. Okay, so that's how many you have each one. First of all, let's back up one section. It says there's 3 isotopes. Yet an isotope is the same element that has a different mass, different weight. Okay, so it's the same element. It's like copper, but there's 3 isotopes of copper. The definition of an isotope, which we'll go over again in a little bit, is the same number of protons, different number of neutrons. Remember we talked about, Bilal asked about AMUs. For protons and neutrons, each one weighs 1 AMU. Okay? So if we increase the number of neutrons, we're increasing the mass of our isotope, of our element. Okay? So every element has the same number of protons. In other words, if you have copper, copper is always going to have 29 protons. If you have magnesium, magnesium is always going to have 12 protons. The number of neutrons can change. Therefore, it can be heavier, and that gives you different isotopes. So that's what an isotope is. And we'll go over that in a little bit too. That's coming up in this chapter also. That's what an isotope is. So we have isotope Le19, Le17, and Le15. Le19, we have 16 out of 50. And what this question is, what percentage or what fraction? What's the question asked?
Determine the percent natural abundance of each of the 3 isotopes.
Okay, so 16 out of 50. What's 16 divided by 50? 16 divided by 50 equals 0.32. And then to get a percentage, we times 100, right? Because percentage means times 100 out of 100. So we have 32% Le19. Le17, we have 20 out of 50. 20 out of 50 equals, let me calculate back here, 20 divided by 50, and then times 100 equals 40. So you have 40% Le17. And Le15, we have 14 out of 50. 14 divided by 50 times 100 to give us our percent is 28. So if we look at LE 19, it's 32%. LE 17 is 40%. LE 15 is 28%. Now, to double check your work, if you add those three numbers together, what had you better come up with?
100%.
100.
Yeah, you better. I mean, that's the whole thing. If that's all you got, it's got to be 100%. 32 plus 42 is 72 plus 28 is 100. And those are your percentages. Percentages is just a fraction of what portion out of the whole entire mass that you have. So if you have 16 parts of it out of 50, you have 32%. If you had 20 atoms out of the 50, you got 40%. If you got 14 atoms out of the 50, you got 28%. Okay. Now, when you're doing that, in theory, you only have to count two of them. Because the third one you can figure out just by subtracting from 100. Okay.
Okay.
Does that make sense?
Yeah, that makes sense now.
Like I said, put it in front of you. If you're a visual learner, just write it down. Just like I did there to start with. 50 atoms, then list each one in, put what you got, and you count them. Other questions on that one? Because we're going to use that when we do average atomic mass. We're going to calculate the different isotopes that we have, and we're going to figure the average atomic mass. If you look at the periodic table, does everybody have a periodic table they're looking at? Okay, look at the periodic table. Can everybody see a periodic table on their book or something somewhere?
Yeah.
Okay, you look at the periodic table, you'll see there's letters and all kinds of stuff. You'll see there's a number on top of every element. That's the number of protons in the element. Okay. You look at the bottom, you'll see there's a decimal number. Like if you look at chlorine, you see 35.45, or oxygen, 15.999, or carbon, 12.011. Those are your average atomic masses. That's what we're going to calculate by using these concepts we just did right now that Cassandra asked about. We're going to use this concept of different isotopes to calculate the average atomic mass. That's where these numbers in the periodic table come from. And we'll be able to calculate those and figure those out. More fun coming up. So that's a really good question. Other questions?
Is it safe to say this will be in the midterm, doctor?
It's safe to say you will have to do a calculation of a element that is so far unheard of. And yet you'll tell me it's of average atomic mass. Yes, you will do that calculation on the midterm. That's a safe assumption. And I'll definitely go through another example, exactly what you're going to be seeing. Okay, other questions?
Yeah, I was just giving more people a chance if they wanted to.
You're on a roll, Cassandra. Anybody else can jump right in too, so it's no problem.
Okay, so my next question is still on the one we were working on, but it's another part of the question. I guess it's just a second part. So
Okay.
So it says Le19 has an atomic mass of 19.0134 U.
19.0134 AMUs. Okay. Those are your atomic mass units. Okay.
Okay, and then Le17 has an atomic mass of 17.4629.
Okay.
And Le15 has an atomic mass of 15.7384.
And
So
they
it's-
want to know the what? The average
Yeah.
atomic mass?
Yeah.
That's just what I was talking about. This is what you see on your midterm. Just what Cassandra was saying right here. You'll get this information. You'll get your percentages. Now you know how much percent you have of each isotope, and you know what each isotope weighs. So now you can do the average weight for each one. So let's do Le19. Le19 is 19.0134. So let's go here, get 19.0134. This is Le19. Okay. And the percentage of Le19 was, where are we at? 32%, right? 30% fraction is 0.32. Okay. You want the fraction of that mass. You don't want the percentage of it. Remember, to go from your percentage to your fractional value, you just divide by 100. Because we took our fraction and multiplied by 100 to get a percentage. Now we divide by 100 to get our fractional value. So we're going to take Le19 and do that. Then we got Le17. Le17 has a mass of 17.4629. And the fractional percentage of that was, what was 40%. So the fractional percent is 0.4. And Le15. Le15 weighs in at 15.7384. And the fraction of that was 28%, so 0.28. So there's your mass of each isotope and the fractional portion of your sample that is that mass. So 0.32 of it is 19, right? So we multiply each of those together. So 19.0134 hit the wrong button. 19.0134 times 0.32 equals 6 point in your two places. So 6.08. We'll round out two places past the decimal since you're adding with multiplying and adding. And Le17 is 17.4629.
6.98516.
6.9, 6 point what?
6.985.
So 6.99, right? Round it up.
Yes, doctor.
Okay. And what's the other one? 15.734 times 0.28.
4.41.
4.41. Okay. So if you take each one of those isotopes, weighs that much. So 32% of the sample weighs 6.08. 40% weighs 6.99. And the other 20% weighs 4.41. So the total weight, the average atomic mass, we add those together. So we get 18, we get 14, that's a 4, and 13, 17. We end up with 17.48 is our atomic mass. And that's how we get those numbers for each of those on our periodic table. That is what you'll do on the midterm. I'll give you an element. I'll give you the percentages. I may only give you 2 percentages because then you can figure out the rest of it. And I'll give you the weight of each one. And you should tell me the average atomic mass of that element. Here. This is Pumpernickel. He always comes back and bugs me. He helps me teach all the time. He just got out of the pool. He's all wet. Dog loves to swim every day. All right, is that making sense? Good boy.
Yeah.
Good boy, go sit down. Go sit. Good dog. All right, so that's a real important question because we'll do another one of these as we go through the chapter, but that's one that you will have to do for the midterm. Something just like that. But that's where these numbers come from in your periodic table, that are the fractional numbers, the average atomic mass. Because we're going to use that when we do calculations, like when we do stoichiometry. We're going to use that average atomic mass.
I have a question.
Go for it.
Well, it's for Cassandra because I'm on the question 29, and I was wondering when she typed in those percentages, did it work? Because when I typed, yeah, when you typed in those percentages, did it mark correct?
Oh yeah, I was actually off by 2 for one of the lightly colored balls, but I was just gonna redo it based off of his example anyways.
Yeah.
Okay.
Because I put like 32%, 40%, and 28%, and it says that they were incorrect. So I'm wondering what I did wrong.
Did you count wrong?
Yeah, it's because I originally for the light colored balls, I counted them, I miscounted them. I was off by like 2 or something.
Oh,
So
okay.
I was just gonna redo it on my own by your example
Right.
anyway.
It'll just do the same thing, but just recount each color balls.
Okay.
Yeah.
Yeah.
So yeah, so just do that.
Yep. Perfect. Perfect. All right. Other questions?
Yeah, I have one last question.
Sure. No, go for it. No problem.
So it's question 32 for chapter 3,
Okay.
and it says, how many protons are in an ion with 36 electrons and a -1 charge?
Okay. So we have an atom has protons, neutrons, and electrons. Okay. If there's a -1 charge, protons have a plus charge, neutrons are neutral, there's no charge, and electrons has a negative charge, -1 charge. Okay. So for an ion to have a -1 charge, it means it has 1 electron more than the number of protons. So if it's 5 protons, there's 6 electrons. If there's 8 protons, there's 9 electrons. That will give you a -1 charge because protons are positive and electrons are negative. On a neutral atom or neutral element, the protons equal the number of electrons because they balance. Positive and negative charge are the same. So if there's a -1 charge, it means you've got 1 electron more than the number of protons. So if you have a -1 charge ion and you have 36 electrons, how many protons do you have?
So it'd be 37 since you're saying it's more.
No? Remember,
35.
35. Perfect, Bilal.
Oh, 30. Oh, because
35.
less.
Perfect. Do you see why? Because it's a negative, you have an extra negative charge. So if you have 36 negative charges, you can only have 35 positive charges because the overall net charge is -1. So you have an extra electron. So you have 35 protons. Protons determine an element. Look at the periodic table. What element is number 35? Look at your periodic table.
Is it bronine?
Bromine. Br,
Bromine?
right?
I'm sorry. It's kind
Oh,
of
no,
faded.
fine. That's perfect. So Br, bromine. What was the question? What did it ask? Ask what element it was?
It asked the number of protons.
Oh, number 35.
Yeah.
But it's
And
Br
then-
minus. So it's 35 protons.
And then it's asking how many total electrons are in Ba2+ ion.
Okay, Ba 2+. How many, what is it asking? How many what?
How many total electrons?
Okay, so how many total electrons? Okay, so Ba 2+. Ba, look at Ba on the periodic table. That's barium. Barium is number 56. Whoops, what did I do? There you go. Barium is number 56. So there's 56 protons. Okay. Remember that that's the number of protons that determines your element.
Would it be 57?
Well, 57 will be +1. 56, that's how many electrons do you have? Now remember, 56 can't change. Okay, so if you have 56 protons, that's fixed. So how many electrons do you have if the net charge is +2? It means you have to have 2.
I was doing +1, sorry.
Right. Well, you're still going the wrong way, though. Think about it when you look at it this way. 56 positive charges. Okay. Now you can't change that. So how many negative charges do you have to have? So it's 2 plus
54.
54. Perfect. You have to have 54 electrons. Because 54 minus charges, 56 positive charges, you have +2. Okay. You gotta remember thinking that the charges have to balance out. You cannot change that 56 because that's the element. Barium is 56 protons, and that determines your element. That cannot change. The number of electrons can change to form an ion. Does that make sense?
Yeah, that makes sense.
Okay. Just remember, protons are always positive, electrons are always negative, neutrons are always neutral. And that's what makes up an atom. And the number of protons is your element. So once you're given the number of protons, that cannot change. Okay, another important concept, which we will go over a little bit more of that too. Okay, other questions?
So basically for the one that we just did, it's just essentially like subtraction, but like in a backwards way.
Right, if you have 56 protons, because that's barium. By definition, barium has 56 protons. So you have 56 plus charges. So if the overall charge is going to be +2, how many negative charges do you have to have? 54, because that we have 2 extra positive charges. Because 54 pluses, 54 minuses equal out, and you got 2 extra positive charges. So, I mean, when you look at your periodic table, you see there's a line dividing like the 1/4 or 1/5 to the right and like 4/5 to the left. All the ones to the left are metals. Those all have positive charges. All the ones to the right are non-metals. Those are negative charges. We'll go over that too in just a little bit. How you can determine your periodic table, what kind of charges you're going to have. And again, the only thing that can make an ion is to change the number of electrons. You cannot change the number of protons, only the number of electrons. So protons don't change. The neutrons change to determine your average mass. The electrons change to determine your charge. But the protons do not change. Because if you change the protons, you change your element. Does that make sense?
Yeah, so just to reiterate, you said protons don't change, neutrons determine the mass, and electrons determine the charge.
Perfect. Because neutrons
Okay.
can change and electrons can change. But protons cannot change. Remember, you look at protons, neutrons, and electrons. Okay, so protons, neutrons, and electrons. we have a mass, and we have a charge. Protons have a mass of 1. Neutrons have a mass of 1. Electrons essentially have a mass of 0. Protons have a charge of +1. Neutrons have a charge of nothing. There's no charge. And electrons have a charge of -1. So again, so you see, looking at that, your protons stay the same. Your neutrons can only change the mass. They can't change the charge. And your electrons can't change the mass. They can only change the charge. So your neutrons change to make your isotopes. Your electrons change to make your ions. Does that make sense? Again, another important question. That's a real good question, Cassandra.
Okay,
Here's
so you
one-
said that, I'm sorry.
Go ahead.
You said the neutrons determine the isotopes, electrons determine the ions.
Correct. Because isotopes are
Okay.
mass, they weigh more, and ions are charges.
Okay. Yeah, I
Yep.
just wanted to write that down.
Perfect. You did my lecture for me tonight. All right, other questions? Everybody else understands everything, right? All right. You want to go over chapter 2 with questions? You want me to go kind of review chapter 3 with you, and then do more questions if you have any?
Oh, I had a lot of questions on chapter 2, so I think it would be better if I just did a one-on-one Zoom call with you because I don't want to annoy people. So
I don't know.
No, please go over chapter 2. I'm okay with it.
Okay,
all right.
so let's
I
tell you
might
what,
have
let me go through chapter 3, get all the highlights for you, and then after that we'll go over chapter 2 stuff. Okay?
Sounds good.
Sounds good. All right. Because the questions you're asking, I guarantee you, everybody else has the same question. I guarantee it.
Oh yeah. I'm not embarrassed about asking questions. I just don't want to take up other people's time if they have other questions too. I don't want to be rude. So that's
No.
why.
Time.
No, everybody's going,
Good,
ooh.
everybody's getting a chance.
That's right. Everybody's
You're
going, I'm glad
helping
you're
us.
asking that.
You're helping us.
All right,
Okay.
so chapter 3 was atoms basically the building blocks for everything. That's what makes up all matter. We talked about the law of conservation of mass. Like we said, we use the example of hydrogen plus oxygen gas goes to water. Okay, we determine that with some of the questions that were asked. If I have 8 grams of hydrogen and I end up with 18 grams of water, how many grams of oxygen had to react?
10.
10, perfect. Okay, has to be the same on both sides. That's conservation of mass. Has to be the same on both sides. Okay. Looking at the periodic table, if everybody pulls up periodic table, like I said, if you look on the periodic table, there's like a black line or dividing line on the right-hand side that kind of slants starting at boron, silicon, arsenic, tellurium as it goes down. Elements to the left of that line are what's called metals. Elements to the right of that line are called nonmetals. Okay. When we're going to combine compounds, if a metal and a nonmetal combine, that's ionic, and we're going to name it a certain way. If two nonmetals combine, that's covalent, and we name that a certain way. Okay. In dealing with the periodic table, we would have we talked about ions. Now, every column in the periodic table is a family. They all react similarly. So everything in column that says 1A, if you look at 1A, it's the left-hand side, all the way straight down. Those will all form a +1 ion. All the ones in the second column will form a +2 ion. Okay? The ones in the middle between the two peaks, basically, the ones in the center, those are transitional elements. Those can have different charges. Okay? Then starting with the column with boron, those are +3. Then the column with carbon, those are neutral. That forms your organic compounds. Then starting with nitrogen, it's -3, the whole column. The column of oxygen is -2. The column of fluorine is -1. So on the periodic table, you got +1, +2, skip your transitional elements, +3. Then you got your neutral column, which is carbon. Okay? Then you get your column with nitrogen with -3, -2, -1. And the column all the way to the right are what's called your noble gases. Noble gases do not interact with anybody. That's why they're called noble. They're too snooty to interact with anything else. They don't form reactions, not even with themselves. Okay? So all the gases on the periodic table, all the gases are what's called diatomic. You see, I wrote it there. Hydrogen is H2. Oxygen is O2. Nitrogen is N2. Fluorine is F2. Okay? They're all diatomic, every one of them, except the noble gases. The noble gases do not interact even with themselves. So hydrogen is He. Argon is Ar. Neon is Ne. Okay? They do not interact with anything. That's what they call the noble gases. They're stable. Okay? We do Lewis structures, we'll learn about why they're stable. All right. So that's how we do with it. That's the basics for the periodic table. What do I want to say? Something else. Okay. The way we write things for elements. If it's only one letter, it's capitalized. Like hydrogen, capital H. Fluorine, capital F. Okay. If there's two letters, the first letter is capitalized. The second one is lowercase. Perfect example, look at cobalt. Cobalt is CO. If I wrote CO, that's carbon monoxide. That's a deadly gas. CO is cobalt. That's a metal. Okay, so when you're dealing with the periodic table, it's real important. If it's one letter, it's capitalized. If it's two letters, the first letter is capitalized. The second letter is lowercase. Does that make sense? So don't make that mistake. Okay, go see different elements. We have nonmetals, metals, and then we have what's called metalloids. That line I told you about, boron, silicon, germanium, arsenic, those are metalloids, which means they're between metals and nonmetals. They're properties of both. Okay, and everything in the same column, going up and down, is what's called a family, and they react similarly. So if you have a reaction, bromine is going to react like fluorine, and chlorine and iodine. Those are the halogens. Those react similarly. Carbon and silicon are going to react similarly. Computer chips, Silicon Valley, right? Computer chips are made of silicon. Okay. Now, the military is using computer chips made of carbon. Those are diamonds. Pure carbon is a diamond. Diamond is the hardest substance in the face of the earth. Anybody used to play with computers and tack nuts, they run fast, they heat up, right? The biggest problem you have with a computer, when you want to increase the speed of your processing power to run those extensive video games, is the computer heats up and they blow. I mean, they fry a motherboard. You got to put fans on them. Okay, so what the military's doing is running completely fast computers, and they're using carbon instead of silicon. Carbon is diamond. You can't melt a diamond. It's not going to heat up. You can run that as fast as you want. You can overclock that tremendously. And that computer's going to have so much processing power because it can't heat up. Diamond will not melt, whereas silicon will. But it has the same properties because carbon and silicon are in the same family. They're going to react the same. So you remember that when you're using the different elements here, they're going to have similar properties. Calcium is going to react the same as magnesium. Sodium, potassium are going to react similarly. They're going to react not exactly the same, but they react in the same way. If you take a block of sodium. Sodium is a metal. If you cut sodium with a metal knife, it'll blow up on you. You cut sodium with a plastic knife, it's very reactive. Sodium wants to lose an electron very quickly. You take sodium, you put it in a glass of water, flames shoot out, it bubbles around, does all kinds of things. Okay? Potassium, bigger flames shoot out. It's got more of a stable core, so it got much bigger reaction. I mean, we took a chunk of sodium, probably, I'd say 8-9 pounds of it, when I was in chemistry at UC Irvine, and we went down to Newport Pier, and we threw a block of sodium into the ocean, about 8 pounds of it. And you would have sworn World War III broke out. There were flames 10 feet high shooting out of the ocean. I mean, it's super cool reaction. Don't do this at home because you'll get in trouble. Okay. Now, potassium would have been a lot bigger. Rubidium, even bigger. Cesium, huge reaction. Okay. If you want to look up something, you can look them on YouTube videos, see how they react. You get very explosive reactions. Okay? The same family is going to react in a similar way. Okay. How we did protons and how we figured out protons, neutrons, electrons. Basically, we took an element, that page down here. Okay. We took an element, we shot off, say we shot off protons from it. Protons have a positive charge. We shot that beam through a magnet. Magnets have a plus and negative charge. So if this is our target here, okay, this beam is traveling through it. If the proton has a positive charge, opposite charges attract, like charges repel. So this plate is negative, this plate is positive. So this proton is going to start to bend towards the negative plate. That's when we know this has a positive charge. If it was an electron, it would have bent upwards. Okay, those are some of the experiments done to determine our charges on protons and electrons. Okay, that's how we discovered the different charges we have on them. Okay. Now, in Rutherford's experiment, they basically took a sheet of gold foil, which is very, very, very thin, and we shot atoms at it. Okay, we take this atom and we shot at this piece of gold foil. Most went through all the way. Some would deflect a little bit. And every once in a while, one would bounce straight back. Okay, the ones that deflected were getting close to the nucleus. Because remember, the nucleus is a positive charge, and the nucleus of the gold in the foil is a positive charge. As it gets close, it deflects it. Okay? If it hits right on it, it comes back. 99.9% go straight through. Most of your atom is space. Okay? So your nucleus is in the center. Your nucleus is protons and neutrons. That's what makes up your nucleus. Okay? The electrons fly around the outer edges of it. Okay, so if you took the size of an atom, and let's compare it to Qualcomm Stadium. Qualcomm Stadium is where they all have motocross races in San Diego. Huge stadium, 100,000 people would fit in it. Right? If you took comparing Qualcomm Stadium, the size of the atom is Qualcomm Stadium. The size of the nucleus would be the size of a pea. So how many times are you going to hit that by shooting peas at that? Very, very seldom. Most of your atom is space where these electrons are flying around it. Okay? That's what you have to realize. There's a tremendous amount of space around it. Okay? And that's what Rutherford's experiments proved on that. When you write the symbols of it, remember we talked about different isotopes. Isotopes are the same number of protons because it's the same element. Different number of neutrons. So let's take uranium. Uranium has two isotopes. Uranium has uranium-230, 235 and 238. So you write in the upper left-hand corner uranium-235 and uranium-238. You could also write it uranium-235 or uranium-238. My writing's not very good here, but that's a 5, that's an 8. Okay. So uranium has how many protons? Look at the periodic table. Uranium is number 92. And if you want to, you can put 92 down here. That's your number of protons. But that never changes. Once you write uranium, you know it's 92 protons. Okay? So there's two isotopes. They both have the same number of protons, same element. different number of neutrons, different mass. Okay, so uranium-235 has 235 minus 92 is 147. Hold on. Let's do it right here. So we got 235 minus 92 gives you 143. So uranium-235 has 143 neutrons, 92 protons. Uranium-238 has 146 neutrons and 92 protons. Oh, 92 is already written in. Okay. So those are isotopes that we already talked about with all the questions that we already did. Okay. So we write the what's called the mass number up in the upper left corner. That is the number of protons plus the number of neutrons. So on an exam, if I write sulfur and I put on 32, 34, how many protons does sulfur 34 have? Find sulfur on the periodic table. So how many protons?
16.
16, right? Everybody see that? That's your number on the periodic table. That's the number of protons. How many neutrons does sulfur 34 have? Remember, the number of protons plus neutrons equals your mass number, which is up in the upper corner, which is 34. So protons plus neutrons has to equal 34 for sulfur, for this one, for sulfur 34. So how many neutrons does that have?
16.
How much?
16.
Not 16. That'd be
18?
sulfur, but perfect.
Oh,
18,
sorry.
right? Has to have 18. And how many electrons does it have? Remember, electrons has to equal protons if there's no charge. So there's 16 protons, 18 neutrons, 16 electrons. Let's do another example. Let's do fluorine. Let's do fluorine 19, -1. Okay, so that's an ion, and it's an isotope. So how many protons, neutrons, and electrons? So how many protons does fluorine 19 -1 have?
9.
9. Remember, protons are always, just look at the periodic table. It has 9. How many neutrons does it have?
10.
10. Perfect. Because neutrons plus protons has to equal your mass number. How many electrons does it have?
20.
Not 20.
20. Not 20.
Because remember, you can't count the neutrons have no charge. If you have 9 positive charges, that's perfect, 10. You have 10 electrons because there's one more than the number of protons. That gives you the negative charge. If we have copper, 2+, and let's put copper at 60. So copper 60, 2+. Okay. How many protons does it have?
29.
It's a transition element, it has 29 protons. How many neutrons does it have?
31.
31, right? That gives you 60 for the mass number. And how many electrons does it have?
27.
27. You're missing 2 electrons. Perfect. I guarantee you'll see stuff like that on your midterm and your final examination. Okay, is that making sense so far? Let's do another one. Let's do gold. Gold's always everybody's favorite. Gold, let's say gold is +3. And gold is 165. Okay. So find gold. Gold is AU on the periodic table. It's in column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 column over, 3 down. Okay. So how many protons does gold have? AU.
79.
No, that's platinum. Gold,
You
platinum is
say
PT, gold is AU.
AU says 7. Yeah,
Was that?
AU says 79 on my periodic table.
Is it really?
Mine
Yeah.
too.
Holy cow.
Yeah, it says it
It's
on the one
79.
that you put on the data packet.
The periodic table I pulled up says 80. That's really weird. This is really off. That's funny. Periodic table shouldn't be different. I'm not gonna use the periodic table anymore. Okay, I'll just use this one from your book. You're right, gold has 79. I guess I pulled this one, it's just sitting on my computer screen and it's on. All right, so how many neutrons does it have?
86.
86, 6 more, right? 7 more. 86. And how many electrons?
76.
76. 3 less electrons than your protons. So 79 is your protons, neutrons are 86, and your electrons are 76. This number is your mass number. That determines the number of protons plus neutrons. And you always know the number of protons because it doesn't vary for every element. This number determines your charge, determines the number of electrons you have. If it's positive, you have less number of electrons and protons. If it's negative, you have more number of electrons than protons by the number that equivalent to it. All right, does that make sense?
Yes, Doc. Thank you.
I lost my place. I go back to the
Think of it as electrons bringing their negative energy.
Their negative charge, yes. Chapter, what was I in? Chapter 3. Just going through that, make sure we cover everything here. We did that, we did that. We got protons, neutrons, electrons. We did that, we're good. All right, calculating the average mass of an element. We did that with the questions Cassandra had, which were great. Let's do another one just so everybody can do it. So on your exam, we'll have a question that says, you discovered, being the great CMC student that you are, you discovered a new element. Let's do Dr. Onium. Okay, you discovered Dr. Onium. Dr. Onium has 3 isotopes. 3 isotopes. So DR, and let's say DR 37, DR 38, and DR 39. Those are your 3 isotopes for Dr. Onium that you discovered. Okay. You have a percentage of 80.93% of DR 37. You have 11.53% of DR 38. And the mass of DR 37 is 37.331. The mass of DR 38 is 38.097. And the mass of DR 39 is 38.993. All right. Now calculate the average atomic mass from these numbers. And you should all be able to do that. It's just like we did with the one that Cassandra asked. It was a perfect question. All right. First step, put everything in front of you. Now you can see it, just like I did right there. Okay. You know you're missing a number. We're missing this value right here. How do we find that? Can we find that number? We know there's 3 isotopes. So if we have so you have each percentage, the percentages all have to add up to what?
100.
100%. Have to. You got 3 fractions of something, it's got to be 100%. So take 100. Let's put 100 in our calculators here. So take 100. minus 80.93. 80.93 gives us 19.07. Subtract 11.53 minus 11.53. These are over 7.54%. If I add those up, double check your work, that comes out to 100%. Right? 10, 19, 22, 3, 8, carry, that's 20 carry. Okay, yep. Perfect. So there's your first part. So far, so good?
Yes, thank you.
Okay.
Yes.
All right. Now we take the fraction of each one times the mass. So we've got 0.8093, 0.8093 times 37.331. We've got 0.1153. Remember, we move the decimal to the left 2 places because we divide by 100 to go from our percent to our fractional value. Times 38.097 and 0.0754 times 38.993. Those are our fractional values for each mass. You're not wrong to put the 0 in front of the decimal point. I always put the 0 in front of the decimal point so you know there's a decimal point coming. Because nothing starts with 0 unless you put a decimal point there. You know, just so you can see the decimal point a little bit better. So we take 0.8093 times 37.331. Right? Yeah. Equals 30.21. It's 4 digits, okay? And we take our next one. 0.1153 times 38.097. 4.39. Okay. And 0.0754 times 38.993. These are 2.94. And then we add all those together. So we come up with 14, 6, 15, 7, 3. So the atomic mass of the new element you discovered of doctoronium, of its 3 isotopes, the average atomic mass is 37.54. I guarantee you see that on the midterm. Not doctoronium, but similar numbers.
I'm just wondering why we multiplied the fractions to the mass of the isotope.
It's a fractional value of it. It's not it's a percentage, but because if you take all the fractional values, it equals 1, and you have 1 unit. So a fraction, that's like if you had 10% of something, it's 0.1. Use a fraction of that. If you had 10% of $1 is a dime, is it 0.10. Okay. You use the fractional percentage when you're doing mathematical calculations with it. Okay. You express this in a percentage to show you the relationship. But the fraction value is what you use when you do your calculations to determine the value.
I'm just wondering why we multiplied the mass.
Okay, because you have this portion, I mean, this mass right here, okay, you have 80% of it, or 0.8093 of that mass. So you have that much in sample weighs 37, this much weighs 38, another amount weighs And you go your percent values of it, your fractional value of it, to determine how much mass you have for each section. If
Okay,
you
that
have four
makes
isotopes, you do it for four different ones.
perfect. Thank you, Doctor.
Okay, no problem. That makes sense. Ask now, because I guarantee you'll see this again. Okay. We got that. We have isotopes we did, the abundance that we did, different fractions. We talked about ions. We talked about neutral atoms. Review that a little bit more. Is that it for the whole chapter? Boy. Let's just review the ions a little bit more, because we're going to be doing that as we come across. All right, so any questions on this before I go to the next one?
I'm sorry, can we do another example like this?
Another example like this one?
Please?
Sure. Let's do. All right, let's make up an element. Who wants to make up an element? How about Harley-Davidsonium? Okay, let's find an element. Harley-Davidsonium. So HD. That's our Harley. There's no HD on there, is there? No, I don't think so. Okay. So Harley-Davidsonium. We have, say, we have Harley-Davidsonium. Let's do. We'll do 2 isotopes for this one, so a little bit different. So we have 2 isotopes of Harley-Davidsonium. Okay. We have Harley-Davidsonium 101 and Harley-Davidsonium 103. Those are the 2 isotopes that we found. Okay. We know Harley-Davidson 101 has a mass of 101.837 grams. We know Harley-Davidson 103 has a mass of 103.409 grams. Okay. In nature, we find that Harley-Davidson 101 occupies 45.37%. What is the average atomic mass? Okay. You have 2 isotopes. Remember, isotopes are the same element, so same number of protons, but different number of neutrons. So Harley-Davidson 101 and Harley-Davidson 103. Harley-Davidson 103 has 2 neutrons more than Harley-Davidson 101. And they're percentages because there's different weights. They're not exactly one, so it averages out depending on the element. So we'll give you the masses, okay, and the percentage. So you know you're missing this percentage, which we can calculate, because the total percent has to be 100. You have to have 100% if you only have 2 isotopes. So if you add those together to get 100%. So this one is going to be
54.63.
54.63, right? Is that what you got?
Yeah.
Perfect, 54.63%. Because if you add those together, it gives you 100%. And now we just take the percentage of each mass and then add those together. So we take, when we're doing our calculations, we get our fractional percentage, which in this case is 0.4537. Okay, times our mass, which is 101.837. And our fractional value for the HD 103 is 0.5463. And its mass was 103.409. So far, so good? Does that make sense how we set it up, Stephanie?
Yes.
Perfect. All right. Then we just do the math. We do 0.4537 46.4537 times 101.837.
46.203.
What is it?
46.203.
46.203. Perfect. And the next one is
56.492.
56.492. Perfect. And then we add those two together. So we have this much mass from HD 101. We have this much mass from HD 103. So the total average is going to be, we add those together.
102.70.
102.70. Okay. And that's it. That's your average atomic mass.
Okay, thank you.
Oh, you're welcome. No problem. Does that make sense now?
Yes, it does.
Perfect. So no one should miss that on the test, right? Right?
I'm sorry, what?
No one should miss that on the test, right?
Right.
Right. All right, let me go over one more thing and that will finish the chapter just with ions and stuff. The big since I'm confusing with ions. And I'm going to make a chart and we're going to fill this in. Oh, what happened here? Come on. There we go. Here's my chart. And we're going to put element, number of protons, number of neutrons, number of electrons. And we should be able to fill all this out. So let's start with an element. Let's pick phosphorus. I don't know if this periodic table is going to be right, so let's do it this way. Phosphorus 32
It's 15. Oh,
minus 3. All right. So if I give you that element, how many protons do we have?
15.
How many protons? 15, right? Everybody see where Bilal is getting 15 from? They see that big number on the periodic table. Thumbs up or yes, head shakes or.
Yes.
All right, perfect. Okay, so 15 protons. How many neutrons do we have?
17.
17. Because our protons plus our neutrons has to equal 32. Okay. How many electrons do we have?
35.
No, use the wrong number. Careful.
Oh.
Remember, because neutrons don't count. You're adding the neutrons in there.
Would it be 28? Or no, 20.
18.
It'd be 18
Oh, wait.
because you have 15 protons here and you have 3 more than that. The neutrons count towards mass. The electrons count towards charge. Okay. So the protons plus the neutrons equal your mass. The protons compared to electrons equals your charge. Don't add those together. There's a lot of students do it. They'll go, 32, and they'll add 3 to it. It's protons. Okay.
Got it.
Okay, so let's say we have, let's do it this way. Let's say we have 25 protons, 23 electrons, and 24 neutrons. All right, now fill it in. Let's do it backwards. Okay. So what would you write for the element?
IN, which is
Mn, right? Manganese. Look at 25. It's Mn. Okay. What would you put for the mass number?
isn't confused because I added 25 and 24. Oh, we have the protons. Okay, my bad. I'm sorry. I'm sorry.
That's all right. Remember, the number of protons determines your element. So 25 protons, look on your periodic table and look at number 25. What does it say? It should say manganese, right?
Yes, doctor.
All right, perfect. All right, so what's the mass number? What number do you put in the upper left corner?
49.
49, because that's your protons plus the neutrons. And what's the charge on it?
+2.
+2. You got it. Perfect. Perfect. Exactly how you do it. So let's do another one. Let's find let's do 17. 17. 18. 35. Okay. What would you write for your element?
Is it chloride?
It would be chloride, Cl. What would be the mass number?
52.
52.
Perfect. 52 protons plus neutrons. And what would be the charge?
-1.
-1, because you've got one more electron than you do proton. So 52 chlorine -1. Okay. Let's do, figure out 2 more here. So let's do, let me make sure the numbers are right between these books. Silver is, that's still good. So let's do Ag plus, and silver is 7 and 30 is 77. Okay. So Ag plus 77. How many protons does silver have?
47.
Thanks, Susan. I'm sorry, how many protons?
47.
47. That way, yeah, 47. Perfect. 47 protons. How many neutrons?
30.
30. That gives you a total of 77. And how many electrons?
46.
46. That gives you 1 positive charge. Perfect. And we'll do one more just going backwards. So just make sure everybody gets it. Let's do. Oh, finally we can do. Let's do. Barium is 56. 50 and 54. All right. So what's the element?
Is it beryllium? No, that's Br.
Yeah. Barium.
Barium.
Yep. Barium. Okay. What's the mass number?
106.
106. And the number of electrons is, the charge. I'm sorry. We know the number of electrons. What's the charge?
+2.
+2. Everybody see where all those numbers are coming from?
Yes, I believe.
All right. So when we're looking, perfect. That's the end of the chapter. So when we're looking at the periodic table, you have the first 2 columns. I am not an artist, so don't hold me to this. First 2 columns. Then you have the middle section. Then you have more columns here. And this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. One more. 6 columns. Okay. This is 1A. This is 1B. This is 2A. I'm sorry. How they label it in your textbook? 1A, 2A. Okay. All right. So every element in this column has a +1 charge. Every element in this column will have a +2 charge when it reacts. The transitional elements vary. They can have different charges. They can be +2, +3, +7, +8. They can have different charges, and we'll distinguish those. The columns in the boron column will have +3. These ones are neutral right here. That's your carbon. They put carbon up here, boron here, and then nitrogen, oxygen, fluorine, and then neon or helium. Okay, these would be -3, -2, -1, and 0. That is your noble gases. So when we're dealing with ionic compounds, which will be later on, we're going to get our charges right from here. So if you want to have like table salt, is sodium chloride. Table salt, sodium is going to be in the first column. It's going to be +1. Chlorine is in the 7th column. It's going to be -1. So it combines +1, -1. It combines 1 to 1. So NaCl, that's table salt. That's where we get sodium chloride from. And that's how we write the names. And that's what we do with these charges. We balancing these charges. It's gonna be a little bit tricky with the transitional metals, but I'll show you how we do it. Okay? So that tells you how things combine in the world that we write the equations for. Okay? These are ionic compounds. Covalent compounds will be a little bit different. Okay? But it's 1 sodium and 1 chlorine for ionic compounds. And that's where we get these charges right from the periodic table. So we're using the periodic table a lot and all the charges that we even talk about. And that is the end of chapter 3. All right, so any more questions on chapter 3? And if you do, we don't, now, if no one does, we can also go over questions in chapter 2 if you have them.
Yes, I have lots of those.
Cassandra will speak up. I think it's great. Your questions were fantastic. They fed right into what I want to talk about. So that was perfect. All right.
That's
so
good.
Yeah. Any questions on chapter 2 by anybody? If not, we'll review some of chapter 3. We can review chapters 1 or chapter 2 or chapter 3. So what are your questions, Cassandra? Why don't you start off?
Well, I have a bunch, so I'm just gonna
Okay.
start off with the
Start with the
so
beginning.
for number 1, and it says write the numbers in scientific notation, and it
Okay.
says 673.5 equals blank times 10a. A equals blank.
Write the number in scientific notation?
Yeah.
Okay, so scientific notation means the number has to be expressed as a value between 1 and 10. So you have to put the decimal point right here. It's be at 6.735, right? It's got to be between 1 and 10. So we're going to move this decimal point 2 places. So we're going to have 6.735 times 10 to the, I made this number smaller by 2, right? I moved it 2 spaces and I made it smaller. 6.73 is definitely smaller than 673. So I've made it smaller by 2. So I've made this one bigger by 2. So 6.73 times 10 to the 2. So where A would be, you put a 2. Okay, that's scientific notation. Does that make sense?
Yes, doctor.
Okay, this is, I guess this is what they're looking for in the equation, the A. The exponent you raise it to.
So is there like a specific amount of spaces you need to go by according to the 10, or is it?
No, I moved right here. I moved this 2 places, right? I went from this position, 1, 2. I moved it 2 places. I moved that decimal point 2 places to my left. If I made that number smaller, then I gotta make it bigger. So this one's +2. You only go by how many places you move that decimal. If the number was 69738.78, I'd move the decimal point 1, 2, 3, 4, 5 places. So it'd be 6.9738278 times 10 to the, I moved it 1, 2, 3, 4, 5 places. I made it smaller, so I made this one bigger. So 10 to the 5th. If I make it bigger, it's gonna be that's gonna be a positive. If I make it smaller, I gotta make the exponent bigger to make, because you can't change the value of the number. You gotta go the exact opposite direction. Okay? So that number just depends on how many places you move the decimal to make this value between 1 and 10. 6.9 is between 1 and 10. If I stopped right here, if I stopped right there, it'd be 69.7. That's not between 1 and 10. If I kept going, made it 0.6, that's not between 1 and 10. Okay, see, sign notation means between 1 and 10, the value number, and then raise your exponent to count for how many places you had to move the decimal to achieve that goal.
Okay, that makes sense.
Okay, good. Perfect. Other questions?
I have a question.
Sure.
Give me 1 second.
Sure.
So convert 3.31 times 10 to the negative third power meters to the equivalent length in nanometers.
Okay, got it. So when we're doing conversions, write down what you're starting with. 3.31 times 10 to negative 3 meters. That's what we're starting with, right? Make our times and put our line. So what goes on the bottom? Bottom has to be meters. And on the top, you want nanometers, right? Now you got to make that equal to 1. Instead of writing n, what does n equal? Look on your chart of data packet I gave you. Look on the chart, n is equal to nano, which is 10 to the minus 9. So 10 to the minus 9 makes this 1. Nanometer is 10 to the minus 9 meters. So this value is 1. You can multiply any number by 1 and not change it. We're not changing the number. We're just converting it to a different unit. So as long as these cancel, as long as this box here is equal to 1, you'll always get it right. And then this becomes 3.31. Okay, remember, when we bring this up, we change the sign. So we got exponents of 10 to the minus 3 and then 10 to the 9. So 9 minus 3 is 10 to the 6 nanometers. And that's how you convert it. Make sure every conversion box equals 1. Make sure your units cancel, and you'll get it right every time. And just do the math, leaving the exponents out till the end, and then add them together at the end. Bring them all up, and when you bring an exponent up, you change its sign. And then when you multiply exponents, you add them together. So minus 3 plus 9 is plus 6. That makes sense to you?
Yeah, kind of. Could you do one more example?
I can do whatever you want. You want to give me one, we make one up.
You can make one up.
Okay, I love doing that.
Okay.
Let's convert. Let's do English to metric, and then from there. So let's convert 3.9 times 10 to the negative 3 feet. Let's convert that into micrometers. Okay. So start with 3.9 times 10 to the negative 3 feet. That's write down what you're starting with. Then draw your line, put feet on the bottom, and feet I want to go to the metric system because that's English. So I know there's 3.28 feet in a meter. So I can go to meters. And there's 3.28 feet per meter. This equals 1. 1 meter is the exact same thing as 3.28 feet. You get that from the data packets. It's right in there. You can do a whole bunch of different ways. I could have converted feet to inches, inches to centimeters, centimeters to meters, meters to micrometers. I could have gone feet to meters, meters to micrometers. There's, I'll do it both ways just to show you there's different ways to do it. You get the same answer. Okay, so now we're in meters. So meters go on the bottom, so they cancel. And I'm looking for micrometers. Micro is 10 to the minus 6. This equals 1. 1 micrometer is 10 to the minus 6 meters. Instead of writing micro, you write 10 to the minus 6. So feet cancel, meters cancel, and you're left with micrometers. So the math, remember I said on the top you multiply, the bottom you divide. So let's do everything except for the exponents. So let's do 3.9 divided by 3.28. That comes out to 1.19. 1.19, or actually 1.12, because there's only two significant figures here. So 1.2, sorry about that. 1.2, and then our units are, you have 10 to the minus 3, and then we bring up 10 to the minus 6, you bring it up, so that becomes 10 to the 6, minus 3 plus 6 is 10 to the 3rd. And this is micrometers. Now, you don't have to do it that particular way. Like I said, I could have gone 3.9 times 10 to the minus 3 feet. I could have gone 12 inches to a foot. I could have gone 2.54 centimeters per inch. I could have gone centimeters, 10 to the minus 2 meters. And I could have gone meters to micrometers, 10 to the minus 6. Okay. So 3.9 times 12 times 2.54, and then bring your exponents. And you get the same answer. There's multiple ways to do it. You don't have to do it the exact same way I do it. Whatever logic your brain follows is the way to do it. And there's multiple ways to do it with conversions. Don't get set up on, you have to do it the way the teacher did it. No, do it however you feel comfortable doing it. If it's more steps, that's fine. If it's less steps, that's fine too. Okay? But if you keep two things in mind, you'll never get it wrong. Every one of these has to equal 1. You're always multiplying by 1. That way you're never changing the value, only changing the units. And then the units have to cancel. Feet on top, feet on bottom. Inches top, inches bottom. Centimeters top, centimeters bottom. Meters top, meters bottom. You do those 2 rules, you won't miss it. Make sense?
Yes, thank you.
Perfect. Was that all right, Talia?
Yeah, I just had to practice it more.
It's very easy watching me do it. I make it look really simple.
Yeah.
I've been doing this for over 40 years. Okay, I've been doing it a long time. You got to practice it. You're absolutely right. You have to practice it. I make it look simple, but once you practice it, you'll be all right. You'll struggle through it, and if you have questions, send it to me email. Just say, "What am I doing wrong?" And take a picture with your cell phone. You know, just take a picture of it. Say, "What am I doing wrong here?" Or, "Is this right?" And I'll gladly go through it with you. Or write them all down on a piece of paper and stop by my office or something and say, "Look at this. What can I do better?" You know, I'll be glad to go over things with you. It takes a lot of practice to do this. Like I said, I make it look really, really simple because I know how to do it. And once you figure it out, you'll do the same thing. But it does take practice. You need to realize that. It will take a lot of practice. Do you want another one or is that okay?
Can we do another one, please?
Sure. Anyone in particular or pick one up again?
We can make it up.
Okay. Let's do. How about if I want to do. If you're going to run a race that is 5.8 miles, how far have you run in, how many millimeters? Millimeters is that? Okay, so you want to convert 5.8 miles to millimeters. Start them off exactly the same. Start with what you're given. 5.8 miles. Okay. Now miles, you can go to kilometers, but I don't know that it's 0.6 on off the top of my head exactly. But I do know there's 5,280 feet. So I just use ones that I know. 5,280 feet per mile. Okay, so that gets me into feet. And feet, I can go to meters. I know there's 3.28 feet in a meter. Okay. Like I said, you could have got there by going to kilometers, but like I said, I'm sure that it's in that data, guys, but I just don't know the number exactly off the top of my head. And then meters go on the bottom, and I want to go to millimeters. Now look at the data packet. Instead of writing M, I can write what? That's exactly the same thing. Look at your data
10
packet.
to
10 to the what?
negative third.
10 to the negative 3. That's what M means in the metric system. And there you go. You've gone from miles to feet, feet to meters, meters to millimeters. And to do the math, multiply by the top, divide on the bottom. Don't make anything fancy or print anything like that. Always just multiply top numbers, divide bottom numbers. Very simple. And just usually circle your exponents, because we'll do those later. So you don't want to forget them. So 5.8 times 5,280 divided by 3.28 equals 9,336.58537. Okay. And that is millimeters. Well, wait, I don't want to do that yet. And then our exponents, and then we bring this up. So what does our exponent become?
A positive.
+3.
Positive. Perfect. Times 10 to the third. And this is millimeters. So there's your answer. Now, that's, you can't read that on your exam. You can't make it that accurate. So we put that in scientific notation. So we're going to move our decimal point. 1, 2, 3. We're moving this 3 places, right? And have 3 places. Have we made that number bigger or smaller?
Bigger.
We've made this into 9.33658,537 times 10 to the something. Okay, so 9.3, is that bigger or smaller than 9,336?
Smaller.
It's smaller. So that means I got to make my decimal point bigger by 3. So instead of 10 to the third, it becomes 10 to the 6th. I have to make that bigger by 3 because I made this smaller by 3. I got to make this bigger by 3. Okay, that means can't change your number, your value. And then I'm only good to 2 significant digits. So I have to cut it off right here. So 9.3, this is less than 5, times 10 to the 6 millimeters. Is your answer. That's the correct answer. Okay. Just when you move the decimal point, just got to count how many places you move it. If you end up making that number smaller, you're going to make your exponent bigger by that same amount. If I ended up making my number bigger by going to the right, I'd make my exponent smaller by the same amount I had to move my decimal point to keep my number the same. Does that make sense, Stephanie?
Yeah, it does. Thank you.
Oh, no problem. I can make these up all night long. I love this kind of stuff. To me, this is fun. Other questions or more of these, either one, whatever you guys want.
I have a question.
Sure.
Okay, convert a speed of 585 miles per hour to units of feet per minute.
Perfect. Good question. Okay. So right now we're starting with, right? 585 miles per hour. Okay. So now we got to worry about two different things. We've got to convert the top number to feet, bottom number to minutes, right? We want to end up with. So let's start with the top number. So what goes on the bottom? So it cancels. What has to go on the bottom here? We're working with the top one first, in miles.
Miles.
Perfect, miles. And miles, I want to go to feet. I know there's 5,280 feet in a mile. Again, that equals 1. And now I've converted miles into feet. Okay, so you know the 5,280 goes on the top and not the bottom. Because there's not 5,280 miles in a foot. There's 5,280 feet in a mile. You make sure this equals 1. Make sure your values always equal 1. So now we're in feet. So now the tricky part here is hours is on the bottom. So now you got to go on top to make that cancel. They have to be on opposite sides. And you want to go to minutes. How do I make this say 1? How many hours a minute? How many minutes in an hour? How do I make that say 1?
60 minutes in an hour.
Perfect. 60 minutes an hour. You know, 60 has to go on the bottom, right? Because there's 60 minutes in an hour, not 60 hours in a minute. And remember, this has to cancel and miles have to cancel. And you're left with feet in minutes. So to do the math, remember, top you multiply, bottom you divide. So you hit 585 times 5280 divide 60. And that should give you 585 times 5280 divide 60. Goes out to 51480 feet per minute. And again, you put that in the correct notation because you can't have any significant digits. So to put in sign notation, you would come out to 5.1480 times 10. And I moved my decimal. Here's my decimal point, right? I moved my decimal point 1, 2, 3, 4 places. So with a new decimal point, did I make my number smaller or bigger?
Smaller.
Smaller, perfect. So I gotta make this bigger by 4. And then I have 3 significant digits. So I round this off to 5.1. That's what I rounded off to. This is bigger than 5. So 5.15 times 10 to the 4th feet per minute. That's a 1. Does that make sense, Talia?
Yeah, like I said, I just have to practice it more.
Right. It does. It's really simple watching me do it. You sit there and go, well, that's simple. But when you do, 2 o'clock in the morning, when you're working it by yourself, it's not simple anymore.
No.
It's not. And I know it's not.
Frustrating.
It's very frustrating. But like I said, try it a couple times, get frustrated, snap a picture with your phone and send it to me and say, what am I doing wrong? And then
Okay.
go to the next one. Okay?
Okay, thank
Don't kick yourself over it. It does take practice though.
I had a question.
Listen,
For Talia?
go for it.
Yeah, which number on the, for the homework is that on? Because I didn't see that in the homework.
Hold on one second. I believe. Maybe number 22, I think.
Is it for chapter 2?
Yeah, for chapter 2.
Okay.
Now, I don't know if your homework values gonna match up the exact same either.
Oh,
No,
I see.
no, they don't. They just put
Okay.
different numbers, but similar questions.
Yeah, it keeps people from sharing answers. I think that's the logic behind it.
Yeah.
So it might not always match up to the same, but they should be the same in principle.
Okay, good.
You might not get the same numbers. All right, other questions?
Yeah, I had a question.
Sure, go for it.
So it says, perform the calculation and record the answer with the correct number of significant figures.
Okay,
And so it has in parentheses 6.5 minus 6.30 over 4.29.
okay. 6.5 minus 6.30 over 420, right?
Yep.
All right, so 6.5 minus 6.30 comes out to what? .2, right? It's 6.5. 6.30 is 0, 2, 0, right? You're only good to the least accurate number to this place. You're only good to 0.2. Okay. Divided by 4.29. So you take 0.2 divided by 4.29 comes out to 0.04662005. Okay. You're good to one significant digits. You're good to right here. So 0.05, because that number is greater than 5. Would be your answer.
Oh, okay. Yeah, I forgot to round it.
Yep. Yeah, remember this is, if this is 5 or greater, it rounds, it makes that number round up. If it's less than 5, the number stays the same. Okay. That make sense?
Yes.
Cool. Perfect. Other questions?
Yeah, I had another one.
Sure.
So this one says, Steve races to the nearest taco stand at lunchtime and sees that his pedometer recorded his peak speed at 85.9 centimeters per second. What was Steve's peak speed in kilometers per hour?
Okay. So you want to change that into kilometers per hour. Okay. So 85.9 centimeters per second. So I would take, let's do that. We have to convert the top number centimeters to kilometers and the bottom number seconds, SEC here, to hours. So let's do the top one first. So what number has to go on the bottom here? It has to be centimeters, right? In centimeters, instead of writing C, I can write what? Look at the data packet. Instead of writing C, what can I write? What does C mean?
10 to the power of -2.
10 to the power of -2. Perfect. That gives me meters, and meters, I can go to kilometers and look at K. K is 10 to the what?
10 to the third.
10 to the third. So now I've gone from centimeters to meters, meters to kilometers. So now I have kilometers. So I want to stop there for my top number. And then my bottom number, I have seconds. I can go to per minute. How many seconds in a minute?
60.
60. So 60 goes on top, right?
Right.
For seconds. And then I want to go, I have seconds
Minutes.
counts. I want to go to minutes per hour. How many minutes an hour? It's also 60, right? So now I've gone to hours, which I want. So centimeters cancel, meters cancel, seconds cancel, minutes cancel. I'm left with kilometers per hour, which is what I want. Multiply by the top, divide by the bottom, and I leave all my exponents to later. So I have an exponent here, I have an exponent here, and those are my only exponents. So let's take 85.9 and do it. Like I said, keep it simple. You don't have to memorize any rules, this and that, just top multiply, bottom divide. So 85.9 times 60 times 60 equals 309,240. Okay, and then times 10 to the what? We have 10 to the negative 2 on top. We bring this up, it becomes 10 to the negative 3, right? When we multiply exponents, we add. Minus 3 and minus 2 is minus 5. So 10 to the minus 5. Okay, so here's our decimal point. I want to move it to make this number between 1 and 10, right? So I'm going to move this 1, 2, 3, 4, 5 places. Did I make my number bigger or smaller by moving my decimal point?
Smaller.
Smaller. So I make this number bigger by 5. Okay. 5 minus 5 is 0. 10 to the 0, any number to the 0 is equal to 1. So our number comes out to 3.09240. Okay, with no exponent. I made it bigger by 5. I made it smaller by 5, so made it bigger by 5. So minus 5 plus 5 is 0. And this is just 10 to the 0 is 1, so 3.09, and I'm good to 3 significant digits. So right to there. So 3.09 kilometers per hour. That makes sense?
Yeah, makes
Perfect.
sense.
Good. All right. Other questions?
I had another one if other people don't have questions.
Sure. No problem. Go ahead.
So it says the volume of a sample of gas is measured as 3353.1 centimeters cubed. Convert the volume to cubic meters.
Okay. Start with what you got. 3353.1 cubic centimeters. Now, you got to remember when you're cubing a number, you got to cube the units and the number. Okay, so cubic centimeters go on the bottom. So that's centimeters cubed, right? I put parentheses here to show the entire thing. So instead of writing centimeters, I can write how many meters. Instead of writing C, what do I put? What is C equal to? Ten to the negative what?
2.
10 to the negative 2. Okay. And that centimeters cancel. And I'm left with meters. Now, you're raising an exponent. Okay, when you multiply exponents, you add them. When you raise an exponent to another exponent, you multiply. So 10 to the minus 2 cubed is equal to 10 to the minus 6. Okay, so when you're raising an exponent, remember, you're raising that by 3, it's cubing it. Okay, so when you raise that, you multiply by those numbers. When you multiply exponents, you add. When you raise an exponent to another exponent, you multiply. Okay, so we end up with 3,353.1 times 10 to the negative 6 cubic meters. Now, in scientific notation, it comes out to, we're going to move this 1, 2, 3 places. So it's going to be 3.3531 times 10 to the, it moved it 1, 2, 3 places, and I made it smaller, right? So make this bigger by 3. So 10 to the minus 6 plus 3 is 10 to the minus 3 meters cubed. That's in scientific notation. If they ask you, this is a perfectly good answer. If they want a scientific notation, you got to put it between 1 and 10. Okay. Just remember, when you're cubing something, make sure you cube your conversion number. It's cubed, that centimeters is cubed. Just don't put 10 to the third. Okay, you got to cube the centimeters and the meters. So that becomes 10 to the minus 6. Make sense?
Yeah.
Okay, a lot of people have trouble with that concept. That's why I just put those parentheses around. It just makes it easier for me to see it when I do it that way. Oops, got my pencil. Oh, okay. All right, other questions?
I'm just gonna ask this question. It's probably gonna be a dumb question, but I've been getting stuck on it.
No problem. What's your question?
I just need some explaining. So you're supposed to do longest length to shortest length, and they give you 1 kilometer, 10 yards, 1,000 inches, and 100 inches. And
Wait. 1 kilometer, 10 yards, 1,000
inches, and
Inches.
then 100 inches.
and 100 inches.
Yes.
Okay, convert everything to the same value. Well, this is, I'll put 10 to the third, that's 1,000, but let me do it this way so it makes it clear. This is 1,000.
Okay.
Okay, so let's convert everything to inches. There's already 2 of them are inches, right?
Yes.
So let's, well, what did I hit? 10 yards. So there's 3 feet in a yard, right? So 1 yard is 3 feet. And there's 12 inches per foot. So 10 times 3 times 12. Okay, this comes out to 360 inches. So this one equals 360 inches. So you got 360 inches, 1,000 inches, and 100 inches. Okay. Now, a kilometer is 0.6 of a mile, right? Well, let's convert it just to be on the safe side. So a kilometer, we're going to go with kilometer. Kilo means 1,000, so 1/3, 10 to the 3 meters. There's 3.28 feet in a meter, and there's 12 inches per foot. Okay, so 3.28 times 12, 36,000. So I don't need to do it exactly. Let's do, because that's about 36,000 inches. A little bit more than that. So this one is 36,000 inches. This one is 360 inches. This is 1,000 inches. and this is 100 inches. So put them in order. So largest to smallest, you said?
Yeah, I get it now. I think the kilometers was messing me up.
Right. Just- What you need to do, we have questions like that. No, it's a really good question. What you need to do is put them all in the same units. Once you're in the same units, just look at the numbers.
Okay. Thank you.
Oh, you're welcome. No problem. No problem at all.
I tried like 4 times on that one. It was really getting frustrating.
Like I said, just ask me and we'll go through it. And why keep kicking yourself over and over? Yeah. So good question.
Thank you.
Good comparison. No problem. Other questions, guys?
Yeah, I'm actually on the same question as she is right now, but since obviously our questions are set up differently, I had a question about mine because one says 1 times 10 to the 11th power nanometers.
Okay.
So how would I convert that
To what? What do you want to convert it to?
to try to figure out the length
Well,
of it?
what units you want it in? What are you comparing it to?
The rest of them are kilometers, yards, and inches.
You got to pick one and go to that. So do you want to go to inches? You want to go to yards? You want to go to kilometers? You got to pick one and have it go to all those have to convert to the same one. So you want to convert this to say inches?
Yeah.
Okay, sure. And then you click convert the other 2 to inches also. You got to everything has to be the same. You got to have apples to apples. So you want to convert, start with your number, and then nanometers go on the bottom to cancel. Nano n means 10 to the minus 9 meters. That gets you to meters. 1 meter is 3.28 feet. 1 foot is 12 inches. And that goes to inches. And again, if you want to do this, save these till the end. 3.28 times 12 is 30. Well, I'll do it first. Let's get the right numbers so you can see it. 3.28 times 12 equals 39.4. Round it up. So 39.4 times 10 to the, and this is 11 minus 9. So these are your exponents. 11 minus 9 is 2. Okay, so 39.4 inches. If you want to put it in like a number, you can put 3940 inches to compare it. Because remember, times 2 means you're going to have 2 places. You're going to increase by 2 places. So 1, 2. Put a 0 there. So 3940 inches is what 10 to the 11 nanometers is. That makes sense, Cassandra?
Yeah, and then I had the other 2 I was struggling with too.
Okay, what was the other one?
So 0.01 of a kilometer.
0.01 kilometers. That's right?
Yeah.
Okay, so kilometers on the bottom. And then K is the same as 10 to the 3rd. It gives you meters. Then 3.28 feet per meter and 12 inches per foot. That goes to inches. So again, take 0.01 times 3.28 times 12. That gives you 0.01 times 3.28 times 12 equals 0.394 inches times 10 to the, we have that left over, to the 3rd. So move that decimal place 3 places, you come 394 inches. They made it real close to the same numbers. It's pretty cool. So this is 3,940, this is 394. That's your kilometers. Again, the key is to get everything into the same units.
Okay, and then for the next one, it said 1,000 yards.
1,000 yards. So what do you put on the bottom? So it's going to cancel.
Yards.
Perfect. Yards go on the bottom. And we know there's 3 feet in a yard, right? So that's equals to 1 right here. And then what goes on the bottom next? So it cancels.
Feet.
So you got this up here on the top. So what will go on the bottom?
Maybe feet.
Feet, perfect. And you know there's 12 inches in a foot. Now you got inches. So 12 times 3 is 36, times 1,000 is 36,000 inches. Not 36.8, 36,000. Like I said, when you watch me do the conversions, I make it look real simple.
Yeah, you do.
I've been doing it a long time. So when you practice, you'll be able to do it too. It does take practice though. So don't be afraid to practice, get stuck, and send me a picture of what you're stuck on or talk or email, no problem. Because like I said, don't go to the end and go, I saw him do it, looks easy. Hey, it ain't gonna work like that. But if you practice and you work with me, you'll get through it. I will gladly work with you to make you understand it, help you understand it. Okay, other questions? There you go.
Yeah, I have one.
Sure.
See where it is. Ethanol is a common laboratory solvent that has a density of 0.789 grams per milliliter. What is the mass in grams of 133 milliliters of ethanol?
Okay, ethanol is alcohol. That's vodka. That's what you drink. Mix your ethanol and waters. Depending on the concentration of water, depends you get scotch, bourbon, whatever you drink. Like I said, vodka, scotch, bourbon, all depends on the concentration of ethanol. But ethanol is alcohol. That's your drinking alcohol. And the density is 0.789 grams per milliliter, right? And it says how many grams is 133 milliliters, right? What's the formula for density? Density equals mass divided by volume. So you're looking for mass. So mass, divide V on both sides. I mean, times V to both sides. You cancel and you get V over here. Mass equals density times volume. So mass equals density, which is 0.789 grams per milliliter times the volume. Volume is 133 milliliters. Milliliters cancel. You're left with grams. 0.789 times 133. Equals 104.937. Which comes out to 103, how many, 3 single digits? 105 grams. Remember, density is mass divided by volume. So if you're given the density, if you're given any one of those variables, density is mass over volume. If you're given mass, you can find, if you're given density and volume, you can find mass. If you're given mass and volume, you can find the density. If you're given mass and density, you can find the volume. Okay. As long as you're given 2 of the 3 variables, you can solve for the other one. That make sense?
Yeah. That makes sense.
Okay, perfect. Other questions? We got any questions?
I have one. I have one.
No problem.
So, okay, since number 39, it says the surface temperature on Mercury has been measured to be 369 Kelvin. What is the temperature in degrees Celsius?
Okay. You didn't say degrees Kelvin, right? You said Kelvin.
Yeah.
Okay, good. So our formula, Kelvin equals 273.15 plus degrees centigrade. Okay, so take degrees centigrade plus 273.15 gives you Kelvin. So if you're given Kelvin, our degree centigrade is equal to our Kelvin minus 273.15. Just rearrange this formula here. Okay. So our degree centigrade, you have Kelvin, which is 369 minus 273.15. And that gives you your degree centigrade. So 369 minus 273 gives you 95. You only get to 95.9, so 96. 96 degrees centigrade.